I mentioned this is going to be part 1 of solving exponential equations. The past few days, the first 3 sets of notes over exponentials, we've focused on the graphs and identifying key features and describing the graphs, all that fun stuff, transformations. So now we're going to focus on the equations and solving the equations algebraically. So we've got the steps listed here in this table. Okay, so it says that step 1 is to use the properties of exponents to simplify each side of the equation. Step 2 is to rewrite the equation so that both sides have the same base. And then step 3 is to drop the base and set the exponents equal to each other. Okay, so properties of exponents to simplify each side, we'll kind of go over those as we get to questions that require us to do that. Some of these, okay, type 1 equations with a common base. Okay, these are the basic ones. These are already set up for step 3. Okay, because you can see both sides already have the same base. This is a base 2 raised to a power. This is a base 2 raised to a power. Everybody understand that and see that? So these are going to start a little simpler and we'll get more complex as we go. Okay, but once you have the same base on both sides, it's I say obvious, but maybe it's not obvious to everybody. It's obvious to me because I do a lot of math. But if the bases are equal, for the equation to be equal, the exponents must also be equal, right? So that's why we're able to drop the bases and just set the exponents equal. Okay, because there's nothing extra not in the exponent. Okay, we've got a base 2 to a power equal to a base 2 to a power. So those powers must be equivalent to each other for this to be true. So in here, because the bases match, I'm ready to set this exponent equal to this exponent. And then it just becomes like a basic, really not even an algebra 1, this is like a pre-algebra question. Just solve for the variable. Okay, so once I get those exponents set equal, I solve using my algebra rules. Opposite operation to move things. What you do to one side, you do to the other. And I get that x is 8. Now, just like with any type of function, doesn't matter if it's quadratic, absolute value, exponential, whatever we've worked with, and whatever you will work with in the future. When you solve an equation, how can you check that it's right? Is there a way I could check that 8 actually works? Yeah, replace it, plug it back into the original equation. So if I come back up here and I replace x with 8, 8 plus 1 is 9, so I have 2 to the 9th equals 2 to the 9th. That's true. I don't even have to solve the 2 to the 9th. 2 to the 9th equals 2 to the 9th. I know that's right. So that works. Okay, so some of you, if it's basic like this one, you're going to be able to do that in your head. You're going to be like, well, if they have to be equal, what plus 1 is going to give me 9? Oh, 8. Right? Now let's try this one. 2 is already set up for step 3 as well. We've got base 5 to a power equals base 5 to a power. So I'm able to simply set those exponents equal to each other. You can think of it as just dropping off the base. So I've got 4n plus 5 equal to n minus 7. Now this one's a little more complex. Oh, that was supposed to be an eraser. Still supposed to be an eraser. Come on. Holy cow. Here we go. So this is a little more complex. Can't quite do this one in your head maybe. We've got to move variables are n to the same side. So I'm going to subtract the n from the right side over to the left. So I've got 3n plus 5 equals -7. And then I'm going to move my constant to the other side. I'm getting n's to the left. I want constants to the right. So that's going to leave me with 3n equals -12. And then I'm going to get rid of my coefficient by dividing it out. So divide that 3 over to isolate n, and I get -4. Now I could check, does -4 make the original equation true? So let's just ask ourselves. 4 times -4 would be -16, plus 5 would be -11. -4 minus 7 would also be -11, wouldn't it? So it checks out, it works. Feel okay about those? Okay, so that's when your bases are already common. You already have common bases. Okay, you just are ready to drop the base. You can get that notes back here. All right, the second type of equation that you may have to solve or be asked to solve would be without a common base. Okay, so when I look at the left and right side of this equation, I've got 7 to a power equals 1/7. Over here, I've got 4 to a power equals 16 to a power. So neither one of these have common bases. So I have got some work to do before I'm ready to set the exponents equal. So this is where it gets into the use properties of exponents to 3. Different color here is your negative exponent rule. Okay, remember, if you want to move a term within a fraction, you can by changing the exponent sign. Right now, what is the power on this 7? Is there a power written here? No. So it's an understood 1. Okay, if there's nothing here as the power, it's an understood 1. Okay, now if I want to move that 7 to the numerator, I would change that power to a negative. So the 7 can move up to the numerator if I change the sign of the power. Y'all remember that exponent rule? It works in both directions. If you start with a negative exponent, like let's say I have x to the negative c. I don't know, pick a letter, it doesn't matter. Okay, if I want to change the sign, I would have to move it to the denominator and make it a positive c. Okay, so you can move a term from the numerator to the denominator by changing the sign of the exponent. And if you don't see an exponent, it's a 1. So I change it from an understood 1 to a -1, and the 7 gets to move from the denominator up to the numerator. Now there is nothing left in the denominator, it'd be an understood 1, so I don't need to write over 1. So now over here, I've got 7 to the 4x plus 11 equals 7 to the -1. So now do I have like bases? Now I have like bases. So I can set the exponents equal. You can think of it as dropping the base if that's how you like to think of it. But I'm going to set 4x plus 11 equal to -1. Now it becomes a basic algebra problem to solve. I've only got one x, it's on the left, so I'm going to move my constants to the right. So that leaves me with 4x equals -12. And then I am going to divide out that coefficient of 4, which is going to leave me with -3. Now I'm going to check. Okay, you can actually write it out to check, or you can check in your head if -3 works up here. So 12, or 4 times 3 is 12, but it's -3. So it's going to be -12 plus 1. That's -1. So that would become 7 to the -1, which is 1/7 using this rule. So it does check out. And you could check that in a calculator if you needed to. If you needed to see 7 to the -1 and 1/7 are equal, you could type both of those in Desmos and see they are the same. All right, number 4. Now I don't have to deal with a fraction this time, so I've got to think of some other way to rewrite my bases, one of the bases, or sometimes both of the bases, so that they match. Can you think of a way I could rewrite 16 as a base 4? I'm not going to, I know what you're thinking, but I can't write it, I'm not going to rewrite it as division. Think in terms of exponents, okay? Somebody said it, 4 squared. So somebody was thinking about dividing, but if I divide 16 by 4, I get 4, okay? But that's because 4 squared is 16, 4 times itself. So I can make the substitution here and replace 16. I'll come to the side and show it. 16 is 4 squared. So I can rewrite that 16 as 4 squared instead. Now here's where you have to remember one of your exponent rules is now I've got a power to a power, right? When we have a power to a power, who remembers what we do? That's another exponent rule we may need to come to the side and review. Okay, when you have a power to a power, let's say we have x to the a to the b, what do you do with that a and b? You multiply them. Okay, so we are going to multiply the 2 times the y minus 3. Now we can do that now, or we can do that after we've dropped our base, because we've gotten our bases to match now, haven't we? They're both a base 4. So I can essentially drop these bases, and this is going to be y plus 2 equals, and then it's 2 times y minus 3. And since y minus 3 is a binomial, it's an expression, I put it in parentheses, because when I multiply those, that 2 is going to have to be distributed to both pieces. So I distribute the 2. It's 2y minus 6. So now I want to get the y's to one side and the constants to the other, and it really doesn't matter which one you'd move first. I'm going to move the y's to the right so that they stay positive. So I'm going to move the constants to the left. And I get y is 8. Now I can come back to the original and ask myself, does this work? So 8 plus 2 is 10. So 4 to the 10th. And we could calculate what that is. And then over here, 8 minus 3 is 5. So 16 to the 5th or 4 to the 10th. And it does check out because if you think about the 16 as 4 squared, and then you have 4 squared to the 5th, the 2 times 5 is 10, isn't it? So it's 4 to the 10th equals 4 to the 10th. So I know it checks out, but you could check it in the calculator to make sure. You're still feeling okay? All right, last couple. Make sure we've got the hang of this. All right, so here's one on 5 where I'm going to have to change both bases, because in the last one, I was able to rewrite 16 as a base 4, so the left and right bases matched, okay, because 16 is 4 squared, but I can't rewrite 8 to a power to be 16. 8 to any power doesn't equal 16. Okay, so that's not going to work. So I have to think smaller. What if I made both of these Okay, so I could rewrite 16 as 4 squared, but is there 4 to some power that's going to give me 8? No, so base 4 is not going to work. Think smaller. 2, somebody said it. Both of these can be written as a base 2. So off to the side, I'll list that when I'm replacing. So I'm going to replace the 16. 16 is 2 to what power? Just go through your head. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 4. So that was 2 to the 4th power. Okay, and then I also need to replace the 8. Oh, that color's hard to see. Let me get a darker green here. Here we go. Okay, 8 can be rewritten as 2 to what power? Not 4. 3. 2 to the 4th was 16. 2 cubed is 8. 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16. So I can rewrite both of these as a base 2, and I'm actually going to rewrite this 4. It's kind of hard to read. Four. All right, so I replace that with 2 to the 4th power, and I replace this one with 2 to the 3rd power. Now that is still to the power of 3x, and that is still to the power of x plus 2. So far, so good? Get a little bit bigger. So now I have matching bases. That's the goal. So I used exponent, replace these to get matching bases. Okay. Now I can drop the bases to set both sides equal. Now when I drop the bases, what do I do with that 4 and 3x? I multiply them. If you need to show that step, it's 4 times 3x. And over here, it's 3 times x plus 2. Show this step. Some of you don't need to. Some of you can just go straight to, oh, that's going to be 12x. And that's going to be 3x plus 6. Some of you will go straight to that step. Now we're solving. So let's move the x's to the left because there's only one constant and it's already on the right. So I've got 9x equals 6. And then I've got to get rid of the coefficient, the 9. I get x is 6/9, but 6/9 will reduce, won't it? What will that reduce to? 2/3. Now you could take this and plug it back into this original to check. Okay, now I would plug, if you're certain that you've done this replacing that I did in the light blue and green correct, just check that the 3x and or the exponents here. You could just plug it back into this blue part if you wanted to, if that's easier to check. If I multiplied 12 by 2/3, that would be 8. And then over here, if I multiplied 3 times 2/3, that would be 2 plus 6, that's 8. So that checks out. Okay. If you want to check it in the original, okay, you can. Most of you would probably need a calculator to do that. You probably aren't so great with your fractional. Actually, this wouldn't come out to fractional exponent. Well, this one would. You would have a fractional exponent over here. So you may need to do a little refresher. But you could use Desmos to check those as well. All right. 6 is a little bit more complex. So in number 6, we don't have a base to a power equal to a base to a power. That's not the setup. Not only do the bases not match, I've got multiple bases over here on the left. It's not just in one term. raised to a power. I've got two separate terms being raised to a power. So now you have to remember your rule of multiplying like bases. So this is another exponent rule that you may need to refresh on. So let me come off to the side and we'll refresh on this rule. If you are multiplying like bases, so both the base x with different exponents, who remembers what you're supposed to do? Whoa, what just happened? What's that? Who remembers what you're supposed to do here with those exponents? Add them. So up here in this one, we said when you have a base to a power raised to another, a power to a power, you multiply the powers. Okay? But these powers have their own individual base. Their bases are the same. See how they're both base 9 over here? Okay, you end up adding those powers. So on the left side of this equation, we can condense this to a single term raised to a power, just 9 to a power. Okay, and I'm going to have to add the exponents. So these are both base 9. They match. That's good. So it's going to be a single base 9, but I have to take 2x plus 4 plus 2x. Yeah, sorry, I had to, my toolbar up here went away. I had to go grab it back. Okay, so then on the right side, I need to make this base match. So up here, where was it? In number 3 here, we said if I need to change this fraction, I want to bring this term from the denominator up to the numerator, I can change the sign of the power, right? So I can do that same thing with 81 here. So I'm going to take that 81 and I'm going to rewrite it. Remember, 1 over 81 is going to be equivalent to 81 to the negative 1 power. So I'm going to rewrite this as 81 to the negative 1. So now I've gotten rid of the fraction. Adriana? Yes, I'm going to. Yes, we definitely want to do that. Okay, so now I'm a step closer. Okay, I've done a little bit of work. I still don't have matching bases yet, right? But I'm closer. I've got a single term base over here, and I've got a single term base over here, and it's not a fraction. So I'm a step closer to where I need to be. Now, what Adriana asked is on the left side, we've got like terms in the exponent here. We've got two x terms. We can go ahead and combine this. So on the left side, I'm just going to clean this up. It's going to be 9 to the 4x will combine, and then I've still got the plus 4. You're adding them, though. You're not multiplying them. X times x is x squared, but this is just 2x plus 2x. So when you're adding like terms, you're just adding the exponents and keeping the variable the same. No, when if you're, excuse me, when you're adding variables, adding and subtracting, the variable doesn't change. You're just combining the coefficients. The only time your exponent's going to change is if I was multiplying 2x times 2x, then yes, I get 4x squared. But it's just 2x plus it. Think of x as just like items. Like I've got $2 and I've got $2. I'm just adding them together. So now I've got $4. Okay, it didn't square what I had. Okay. All right, now on the right, so I've condensed this, cleaned this up a little bit on the left. Now on the right, I want to rewrite this so that I have matching bases. Can I rewrite 81 as 9 to some power? What is 81 is a factor of 9, not 6. What times What 9 times what gives you 81? Not, it's a perfect square. 9 times 9. So 9 times 9 is 9 squared. So because 81 is the same thing as 9 squared, I can make this replacement. I'm going to replace that with 9 squared. Now that does not mean that -1 power goes away. It's, yep, I'm going to have to do 2 times -1. So it's going to be to the -2 power. Now I've got matching bases though. So now that I have my matching bases, I can drop them and just say, okay, 4x plus 4 must equal, and then we're multiplying these, so that's -2. I've only got one x term on the left, so I'm going to move my constants to the right. I have -6. And then I divide out my coefficient. Doesn't divide evenly, but I can reduce the fraction again. And that would be -3/2. Now I could take this and I could plug it back into the original to check. So I'll show you Desmos on this one because this is a pretty complex one. So I'll pull up Desmos here. And we'll check it. I'll show you what that looks like. All right, so if I want to check this, I'm going to do the left side, which is 9 to the power. Now remember in Desmos, when we're entering multiple things in our exponent, like an expression up here, we've got to have parentheses. So I'm going to put in parentheses, and then it's going to be 2 times, and I'm plugging in -3/2. So 2 times -3/2 plus 4. Well, if I so apparently if you calculate this, it ends up just because you multiply that, the 2's cancel, you've got -3 plus 4, that's 1. So 9 to the first power is just 9. So we probably could have done that one in our head, but you can confirm it in Desmos. Now the right side, oh, sorry, that's not the whole left side. We're multiplying all of that times 9 to the 2 times our -3/2. Okay, so we get an ugly decimal here for the left side. Okay, so this is what the left side comes out to. Let's see, the right side is 1/81. Let's see if that's the same. Are those the same? Yeah. So our left side, the way it was written, does indeed equal the right side when we plug in -3/2. So that confirms that I've done it correctly. Y'all feel okay about the algebraic process of solving? All right, now let me show you something fun. You're gonna be happy I showed you this. Let's go back up, maybe to one of the basic ones. It's a little easier to type in. And let's see. If I type in 2 to the power of x plus 1. Now, I want to graphically solve these. You need everything to one side. So to check it graphically, I would have to move this term, this 2/9 would have to move to the left side. Right now it's positive, so I'd move it by subtracting, right? Oh, and that +1 didn't go in my exponent. See? It's supposed to be in my exponent. Remember, if there's anything extra up there, you've got to use those parentheses. So that +1 is supposed to be in the exponent. Now come out of the exponent, and I'm going to do -2 to the 9th. And I just get a vertical line. Where's that vertical line? What was my solution? So you can check your work this way as well. Okay, now to check it like this, to see that, you have, like I said, you have to have everything to one side. Okay, so I had to move that whatever's on the right, I had to move it to the left. So if I did that with a more complex one, here with number 5, let's try it. I have 16 to the power of 3x. And then I would subtract this 8 to the power of x plus 2. Look at where that solution is. Do you see it? That's 2/3. If you need to see 2/3 as a decimal to confirm that, just type in 2/3. 0.6 repeating. And that's where the x-intercept is showing here as well. Does this make sense? So if you want to check it graphically, okay, you're going to get this vertical line through the solution by putting everything to one side and typing it in like this. Okay, so that's a way that you could check it. Okay, or of course, you can just check like 16 to the power, and we said that it should come out to 2/3. So I'd plug in a 2/3 for x. So that's the left side, 256. And then check the right side, 8 to the power. And we said it should be 2/3. And then that's supposed to be plus 2. Also comes out to 256. So the left side and the right side, they come out equivalent when I plug in 2/3. So that means 2/3 is the solution. It makes the equation true. Yeah. Okay. All right. So we have gone through the algebraic process of solving. We had to refresh on some of our exponent rules. I tried to write all of those in red here to color code that for you. Okay, but this is your process. Okay, we've got some basic examples and then some more complex examples that you can refer back to. Okay, and then you can use Desmos to check your work. Make sure you've done it correctly. All right, so I'm going to go activate the practice for y'all in Delta Math, so you can try some of these on your own.